Alright. That's probably loud as fuck, huh? Alright, let's go. Working on an operating system again. So last night I was working on the shell, trying to get dynamic memory. We got that kind of working. Now we need to be able to access the file system. So, first thing I need to do is I need to go back to the utility I have for writing on a file system, and I don't think I really totally finished this. So I have a... This is nice. This is what the file system looks like on disk. So what I haven't done yet is write out the inode table. I realized that I never did that, so I need to do that first of all. And then on the kernel side, it needs to read that in at boot up and have like an in-memory version of the inode table. And then you just start implementing system calls like open and read. And have like the kernel data structures that manage file I/O basically. So let's do that. Well, let's do this. Let's go into here. And where we write, this is write entry, write superblock, right. Alright, so this is writing the whole image to a file, right? So here's what we have. We write the inode bitmap, we write the data bitmap, we write the data region here, and the superblock, but not the inode table. So the reason we do these after that is because we need to know how many blocks we've written. What do we need to know to write the inode table? Well, I mean, we have this global array of inodes, so we should have everything we need. Except, does the inode contain like its size? Probably, right? Which we don't know yet, so we will need to do that after we write that out. Where's a disk inode? So you need its size in bytes, which we don't know until we actually like read it from the host system. So yeah, we need to do that after this then. And how does this work? I haven't been in here in a couple days, so. Do we get the size? So this is when we're building the inode table. This is disk image entries and dir links, but where's the inode get like initialized? Who calls that? So all we're writing is the type. Yeah, so oh, that's just if it's a directory. If you're inside a directory and you find that's a regular file, well, then you do write the size. So we have it already. Good. Great. So here we can write it out in like actual, like the order it actually appears in the disk image. So we write the inode bitmap. We can just write the inode table here. So disk image write inode table. It's going to need the file to write into, and then inodes, and we'll give it the length, I guess. So where's this at? Well, I guess we can return a bool. Write inode table. The inodes and num-inodes, which could be an int, whatever. So what do we need to do for the inode table? We just loop through the inodes and write them out. So what's in these things? You have a type. Alright, and we're saying each one's 64 bytes because that's how we like spaced out that we have a inode table that's the size of a one block, so 4 kilobytes. So does that make sense? Let's see. We have 4 kilobytes. Each one's 64 bytes. That gives us 64 of them. Hold on a second. Something seems... Right, yeah. So the inode table itself is 256K. That makes more sense. So if we take that divided by the size of a single inode, which is 64 bytes, we have 4K. Yep. So that is right. So we have a type you have the how many data blocks you're pointing to and the size. So let's write one of these out. So let's seek to the inode table in the file. So we're gonna kind of do something like this. We're gonna seek to inode table start. And then in here, for each inode we encounter, we're gonna write inodes at I. What's gonna happen for? We have like a empty one. I guess it's just gonna write zeros in there since it's uninitialized. Sure. So for each one, we could just start at 1, but whatever. You can write zeros, that's fine. We write that inode. Its size. One of them into this. If you fail, we just fail. And then we need to seek forward again because this isn't actually 64 bytes. So we have a few options. We could pad it out, or we call seek again. How should we do this? There's already padding here, right? Because you got 16 bits, these are 32, so there's already going to be 16 bits of padding right there. What do I want to do? I mean, the advantage of padding out the struct is I don't have to seek. Yeah, we should probably... Damn it, I don't know. The other thing I'm thinking about is... like... in the kernel, when you read these, you kind of want to have like the same data structures so you can just read them directly. Although there's only 4 members, so we could pick those out. I hate that this little gap's here. We could do something super lame and just do this. Gap gone, alright. Or honestly, just go crazy with it, right? Well, now we have 16. And then we can just pad out the end. So let's see, we have 48 bytes. Bytes of padding. Should we like tag this with like, does it matter? What if we did this 12? So this could be 4 byte line. Do we need to pack? It should be anyway, right? Default, because you're gonna have whatever the largest element is, which is or what does it do with arrays? Well, if we do this, we'll be sure. And now we don't have to, well, we can keep that note. Alright, we'll go with that. So now we can just write these. Easy as. Alright, I know table written. We need a copy of this. Maybe we should, let's, yeah. So if we run this on the disk, it wrote out a disk image, right? So it wrote this image. Let's try to read it in. This thing build? No, because we were fucking around. Well, we could still use the old. How does this? Alright, we're done with this for now. How does this thing execute? This is like our. Okay, well, let's just clean all this up and start in the kernel now. One thing we could do is like open that in a hex editor, jump to like the inode table start and see if anything in there looks reasonable. What's the hex editor I've been using? This one. Alright. Open this one. This is probably super, this is tiny for me, it's probably super tiny. How do I change the size? Not that. Like the UI size. How do I? Settings. Interface. Scaling. It didn't do anything. The fuck? Why is nothing happening? Two times scaling. Oh, I see what happened. Last time it didn't work because you had to close the whole thing. Alright, this is a little better. Alright. That's better. I feel like this is huge, but whatever. Can we... I guess we need like... Oh man, this is huge. Just so we can see that. Okay, we need to go to... starts at 16 kilobytes. Go to address, what is 16 kilobytes? Alright, so this should be the inode table start. The first entry is empty. I mean, we're seeing stuff here. A type. 1 is directory, 2 is file. So like directory, directory, file. This file is... Well, hold on, what is... Let's see, it's Little Indian, so this is the beginning. So that is type. Num adders, we didn't write that either, did we? Huh. So, oh wait, it's type. Wait, no, that's right. Type num adders 0, and then size 101 bytes. That, I mean, makes sense. But why is num adders shouldn't be 0 if it has a size? Do we have another file? This is a file. Size in bytes. Is this? Oh, wait. When are we writing no matters? So I think we're missing this. Go back down to, we'll rotate these. Go back down to here. It's actually when we do the traversal, I guess. So where do we write the inode? Bergstrom, what's up? This looks like fun. It is fun, yeah. Having a good time. Trying to learn how operating system works. So we're gonna write one to do that. Where do we write into the inode? So here, we push this. We only write the type and the size. We're not running how many data blocks. But we should know that here too, right? Because you know the... Well... We know the size. We know the size of a data block. Just thinking, should we write it here? Or wait? I mean, when we... The other place we can do, which we might be better, is when we write an entry, we actually read the file from the host system. Data and data size. We write it. We have blocks needed. See, I mean, we can do something like this here, can't we? Yeah, we're already asserting that we have enough size for it. Oops. So we can do... Why don't I have highlighting in here? Some weird thing about... Notice that, like, if you have a different buffer open and now it highlights, that shit is so weird. So if we line up the entry size by block size, divide it by that, that's how many blocks we need. What do we call that? Num adders. Let's start breaking this. Num adders is blocks needed. Yeah, this moves here. Type size no matters. Adders. Duh. Like, we should do this later because we need the actual pointers to the data blocks anyway. Of course we do. So we'll do it here. So when you write an entry, So you need the number of blocks needed for both. Damn, this kind of sucks. Like, I only need to write to the inode table here, but I don't want to compute blocks needed twice. Wait, what is this? This doesn't make sense. Oh yeah, we have to do it in both cases. What am I thinking? That's the whole reason this is like uniform, because yeah, they're the same. So, yeah, we do this, then we say, we have the disk image entry has the inode number, so right, the entry inode num, that's the inode. So let's just pull it out, set the num adders to blocks needed, set the where are we setting all the addresses? Well, the offset is, that's what it is, it's the offset. What's happening over here? Hearing sounds. Redline, what's up, dude? How's it going, man? Yeah, so let's do this after we get the offset. So then you can set the first one. Where do we loop? Alright, they're all consecutive. So we can just loop through like blocks needed, I guess, which is unsigned. The night he started streaming, dude. Yeah, I mean, honestly, I just turn it on sometimes because it keeps me focused. Yeah, I hope you're doing good too, man. Kind of sucks. I'm not really going to. I'm in Seattle anymore, so I kind of don't see people, which is lame. But glad to see you, man. We'll move through what we're doing. Okay, we'll go through how many blocks needed, and just write those offsets into here. So Might be someone to fill that void soon, really? Is like better software conference gonna come to the US or something? That'd be tight. Or maybe Handmaid's gonna do their own thing, the network. What was I doing? Yeah, so let's say adders that I is the starting offset plus I times the block size. Makes sense to me. I already have that loop further down. I do. I'm an idiot. Thank you, thank you, thank you. Yeah, so after we write, then we fill it in. Oh, so we do have this? I just didn't write the Oh man, I already filled this in. So wait, why wasn't it showing up in the when we were looking at it? Interesting. Why was that? Yeah, we are writing that in, so maybe it did show up. Let's verify that. We're not in. Where are we? Okay, we'll build that. Yeah, let's do this on what? This. Hold up, I think I might know what happened. Well, no, it wrote it here. I was thinking maybe it was writing it out here. Because, yeah, that's previous, so that's not it. Alright, well, let's see. Reload this. And let's see. Let's put this over here. Type, no address, size, address. So this should be the first. This is a file. Type, num adders, size in bytes. Why would this not show up? None of these seem to have a number of adders. Doesn't seem to be writing them out. Let's look at where we write them then. So yeah, we're definitely writing it in here. Yep. Right on a table. I should run over here so I don't block it. Well, do we have... This is actually, let's see. We can just look it up on here, right? Wait, what are you saying? Shouldn't you write the inode data structure after setting the adders? Do we not? Right, we're writing the inode table before. Yeah, that's the question I was asking myself before, but I came to the wrong conclusion about it. You're right, thank you for that. Yeah, this is where we set them, so... We're just being dumb. I'm just being dumb. Alright. Did we rebuild? I don't know. Build it. Yep. We got data now. File type 2. Whoa. Alright. We have a type. We have a number adders. 1. Makes sense. Because the size is only 20 bytes. And these are the offsets. First one is here. Seems plausible. This is a directory. That doesn't really seem to make sense, does it? Oh wait, no, it's not. That's not a directory. Yeah. Alright, well, data seems plausible now. So let's see if we can start reading this in and using it in the kernel. Alright. Where are we at right now? We can back out. Okay, so when we initialize a file system, init, so we read in the super block and that's about it. I mean, we check the number of inodes to see how many we have. Should we read in the inode table when you initialize a file system? Probably. Just store it in memory. We're gonna be using that. I think so, but I don't even know if we have a inode in the kernel. Let's see. Let's see. A disk, or no, it's inode here. We do have an inode. Why would you store the inode num in the inode? The num is like the index. That's weird. Maybe this is from like old. I have no idea why this stuff is here. Copy of on-disk inode, which we've now changed, which is why you don't want to do this. You don't want them in two places. These should really share the same. I don't know, whatever. For now, we're just gonna do this. I mean, we don't really want to store 48 bytes of padding in memory, but they're only 64 bytes. For now, we'll just say fuck it. So this is an on-disk inode, just because this makes it easier to read. I can just read directly into this. Well, no, I can't, can I? Unless I keep this as like a different. Like I could just have disk inode, read into that, and like copy it over to the in-memory version. Or are they gonna have different fields? That's a question. So I was trying to read a little bit today about like how I want to handle this. Just reading in like how Linux does it. And so I'm gonna need like three data structures that the kernel needs to maintain. You need the inode table, which is just a list of these inodes. You need an open file table, which we kind of have sketched out here too. Both of those are system-wide. And then a per process like file descriptor table. The file descriptor is just like, you know, you give back applications a file descriptor, which is an index into this table that maps you to open files in this here open file table. Wait, I thought I... put this somewhere else and call this something different. Open files, yeah, you have this open file table. Why is this in here? Oh, all this stuff is old, cause yeah, this is old too, cause yeah, I think the very first version of things I was just putting whatever in there. We're not gonna use that, and we're gonna change this too. But anyway, what I was saying, you need an open file table, and then the inode table. And I think, did I take notes about the items we want? Yes, I did. Right. Which doesn't help us much. Anyway, I don't think we're gonna need that. That's dumb. So how do we want to read these in? We do need, like, where do I make it? Just another inode table, which we do have here, yeah. So we're gonna have an array of these inodes. This is our inode table. I don't know that we need anything different than the on-disk one, right? Maybe we just use the same thing. That would be super convenient. We can start with that, and if we need other shit, we can deal with it. Alright, so let's start reading into this. File system init. So here we read the super block. Here. So let's just basically do the same thing for the inode table. So the thing I'm wondering is, like, the super block tells you how many inodes there are used. But we probably have to consult the inode bitmap to say which ones are used. Because, like, we know, because we just wrote it out, that it's all, like, sequential, but once we have, like, actual, like, once the operating system is using the file system and moving stuff around and stuff, that won't be true anymore. So we need to do something, I think, like find out which inodes are being used, or let's see, should the in-memory version of the inode table have a flag that says whether it's used or not? I mean, you're duplicating data that's in the bitmap, but I'm not quite sure, like, how we're gonna be using all that. Could just start by reading them all in. You know, only like, how many files do we have right now? Not that many are gonna be used. Let's just read them all for now. Actually, no, we're not. It's, what's our, I mean, I know it's 4096, but what's the, files max? Files max what we use here, but it's a little confusing because It's kind of used for multiple things, but all right. We're going to read into this, right? So what do we do? Honestly, we have reading by block, so we could read the entire block directly into the inode table, right? So we don't loop, we just read the whole thing in. That would be convenient. So let's read into inodes. What is disk read block? Like which block to read? How does this work? Yeah, which block? So which block is it? Well, oh wait, it's not a block, it's multiple blocks, so we actually do. So maybe we should read. We're gonna have to read multiple chunks. Yeah, yep. How many blocks is the inode table? It's 272. 64 blocks. Okay. Well, let's do this. Just do. Should we do? I'll just use that. What's I need like the block ID of the start, which is what? This. It starts at 4, which makes sense, right? That's 0, 1, 2, 3, 4 blocks is where it starts. I don't like the magic number. Inode table block ID, I don't know. Well, block is less than. I mean, or we could do it where we just, how many blocks did we say there? There's 64 blocks, so we just add. First block. Oh. So where do we read into? Should we read directly in, or we could read into Yeah, because you just give it an offset. So like how many inodes will fit into, what do we have, 64 blocks in one block? Um, I mean, since every other num's gonna be unsigned, we'll just do this for so it's clear. Um, should we rely on that? So it's like, I know that it's 64, but we should do that. Okay, so we read. Right. It's a little scuffed. That makes sense to me. Well, I guess we can initialize the file system and we know they're going to be the first couple. So this sucks because now I'm in my own operating system. We no longer have a debugger. It'd be nice to just look at it. We could just have printf debugging. So I can just print out like some of the inodes. Like, I don't know, 10 of them. What do we want to put? I guess just like type. This size, you know, I guess that is enough to verify. I'm not really feeling this jam. You know what? Let's listen to. I don't know how loud this is for you guys. It's kind of quiet, but I'm gonna crank it. Be careful. Alright. Well. That's the jam. Whoa, what's happening over here? Volume's good? Okay, good. Well, maybe I'll push it up a little bit then. Alright, what are we doing? What are we doing? What are we doing? Whoa. Well, let's try to print these out. So, we have pipe, blah blah. Adders, size and blocks. Let's dump these here. Okay. Oh man. Before I can even run this, I gotta delete all the bullshit I was playing around with. Alright, in the shell. Yeah. Let's just not even do. Just delete. What's going on in here? Yeah, none of this. Man, let's just see what we got. It's run in here, right? Alright, so everything we were doing about this gotta go. We should clear out all these old bullshit read file stuff too. These are dead. Let's go to syscalls. These are probably gonna get straight deleted. Do this for now. Let's see, what do we miss? Okay. Don't care about any of this stuff. Just none of it. None of it. Okay. We don't have block size in the kernel? Oh right, I think we call it, why are we in visual mode? Disk block size. Yeah. And then size in blocks. Size and lights. Alright, we're not initializing inodes. So we're fucking something up again. Alright, let's see what we did wrong. Probably this like bullshit pointer math right here. So we that plus the size of a yeah. This is dumb, but all right. Wait, no, that's right, because it's pointer math, so that's gonna. Why? Right. Wait, where's... Why are we in the shell? I don't think we have memory for this. Interesting. So we're gonna need... Do we need to allocate pages and store it there? Because we are, I think, gonna map like the inode table. Is that gonna get mapped into like each process's address space? Regardless of where we store it, we need to read it in, so hold on. How does this work? Read into, you know, I'm not seeing it. Oh, I'm so dumb. We're not using the right disk image. Damn it. Right. How do we do this on fucking Windows? That's the one. I should have copied it, but whatever. Yeah, so dumb. Okay, so, you know, we got a directory file of this size, which I remember from... Turn it down a little bit. Yeah, I remember this from looking in the hex editor. That seems right, that seems right. So I think we're reading a file table. That's cool. We'll believe it for now and move on. So that's one of the three kernel data structures we need. So it might be worth... This is kind of what I'm looking at. It's gonna focus. I don't know if that's focused or not. These are kind of data structures we're going for. So, we need a file descriptor table. This is Linux, the programming interface. I bought this a long ass time ago, but it's actually kind of useful when I'm like, you know, trying to learn about how an operating system works. It's like pretty high level. It's not about implementing an operating system, so like a lot of the stuff I want, like the details, like aren't really in there. Yeah, you got this one? Yeah. Yeah. The other ones I'm looking at is here, this one. This right here. Wait, where'd it go? Where'd we go? Operating system 3 easy pieces. This one has, you know, a lot of great information. This is where we got the, like the file system is from this book. VSFS, very simple file system. Yeah, so this is our file system. And then, the other book, this one, Computer Systems Programmer's Perspective, has a bunch of information that's super useful about like how virtual memory works, and my implementation of malloc was like largely from that. Yeah, so that's what we're using. Okay. So if we have a inode table, we can start thinking about opening files. So let's think about this. When we do Alright, the use case we're thinking about is the shell, because that's what we're trying to make. So when the shell wants to open a file, it's going to issue some kind of system call. Open, open system call. Syscall open, which is going to, you pass some flags in that says, are you trying to, open an existing file, create a file, maybe something like that. The kernel's going to need to figure out if this file exists. To do that, it needs to start walking through the inode table basically, and then looking at, so you have a a root inode number, and the root inode is like the root of the file system, which is slash. We start there and just start traversing through the inode table until we find, for open you specify a path. Yeah. So as you go through the inode table, that gives you pointers into the data block. So if it's, the directory data blocks have this stuff, like a dir link. It's basically, does this not have the type? That's kind of interesting. That's kind of interesting that dir link doesn't have the type. Shouldn't it? I mean, you have an inode number, so you can go back to the inode to the inode table to see its type, but why don't you have a type in there? It's a little weird. Anyway, so yeah, you're just gonna traverse through, starting at the root, go through the inode table, looking at path, sort of building up the path, I guess, as you go, seeing if it matches along the way. If you find a match, then what? Well, then you're going to, I guess, allocate an entry in the open file table, which isn't really allocating because we're just having a static array of the max open files that you can have. So you add an entry to the open file table, and then, so the thing that gets returned from the open syscall is a file descriptor. So you also need to, in the process, I guess in each process needs a file descriptor table. So let's look at a process. This is a process right now. We need to add a file descriptor table. How do we want to do that? Do we make that static too? These things are getting, I mean, we shouldn't maybe, but we'll start with that. So what's going to be in a file descriptor? I mean, I guess it's just basically a pointer to, or a pointer, it's just the index into the open file table, right? So do we need any other data with it? I mean, we'll start with no. So how many of these can we have? How many file descriptors can a process have? It's going to be a pointer. It's an array of file pointers. And then I guess you're gonna have what do we call this? Descriptor. Maybe you don't need any flags unless you're inputting close on exec. Right. At least not to start with, so to start with we'll do, what do we call this? I don't want to call it files. It's confusing. Like descriptor table, which has like, what's the max we should use? I mean, we could use file max. We could use the same as like open files max. I think we have one of those. What is it called? Sys open files max. We can use that for now. Kind of makes sense, because that means you could have, well, yeah, you can have as many descriptors as you can have open files, but you can have multiple descriptors that point to the same file, but, you know, these are details we're going to work out. So, each process is a file descriptor table, boom, implemented, kind of. We got open file table, right? Open files. I suppose we need to know how many are in here. The other thing is, like, do we do the Linux thing and have 0, 1, and 2 be like reserved file descriptors? Probably. Well, descriptor table or empty table? Naming is hard, right? I mean, let's do this. So, we got all those. Now we gotta link them all together, I suppose. So, let's start looking at what like a open system call is gonna look like. So system call. Let's put a wrapper in like the user space. What is this? Elemental Magics. Master Elemental. What's up, dude? How you doing? How you doing? Alright, so you're gonna have open, which returns a file descriptor, which is just an index. Which takes a path, some flags, and train to become a grandmaster of what? Magic or programming. Open takes a path. Flags. Am I just like spacing? Well, it's open. What else is... Doesn't it take another parameter? Right, mode. Mode. And the other question is like, do we just copy Linux or do like do my own thing? Seeing as though I have no fucking clue what I'm doing, I'll just start with that. That'll just help us learn. Mode. It's gonna be a syscall to open, and then we just pass path flags mode. What the heck is this? What am I looking at? Nah, dude. Nah. Dang it. Alright. Programming. Me too. I'm trying to become a grandmaster. Alright, what else do we got on here? We need a syscall for this, so what do we have? Like handle syscall. So our arguments are in these registers. Put the return value in A0. Right. I hate how like Vim really doesn't like when you do case statements with scopes. Syscall open. Well, let's pull out A0. A1 and do I have to cast these? Probably. Aren't they already in the trap frame? Aren't they? U32s? Okay. So you have flags, you have mode A2. Okay, so what do we need to do? We need to start at the root inode and I guess start building up a path and then comparing that with the path they gave us. I mean, obviously we want some kind of like caching of that eventually, but right now we have nothing. So you have to do this kind of shitty, slow thing. Alright, well, let's just do that. Let's walk the inode table. So let's see. I guess we'll do this. Root inode num. Files max. It's not it's inum. Could just use I for that, but whatever. I think I do. Do we need a pointer? These things are pretty small. Whatever. Okay. Okay. Bedtime here? Yeah, it's like, what was it, 12:30 here? Cheers, man. Thanks for stopping by. Thanks for helping me with my, what was that? You caught some bugs for me. Thank you. I'm just me being dumb. You catching it. Appreciate you. Have a good night, Holmes. What do I do now? Now that you're leaving, I'm gonna have bug reading code. It's terrible. So we need to build up like a. We need to build up a path and compare it with that path to see if we found it. How do we want to do that? Well, we can say we do have this like where do we do that? Is it in the file system? I had like a path. I don't have these like copy path or join. Path join. We don't have those. Might have to implement that. Right. You need to look at his type. this is actually kind of like the traverse dir that we did when we're building a... Because you're not actually going through the inodes. You're starting at the root inode, and then you're going to say, all right, look through all of its children. And then you go from there. So it's not a iteration through all of the inodes. It's like more of a breadth first sort of deal. So you do need to look at the root inode though. So inodes at root inode num. So we start at the root. We then, well, we need to read that, right? So there's a bunch of ways we can do that, but we're gonna need to end up calling block. What was it? Wait a minute. Disk read block. So, how do we want to do this? What I'd really like to have is like some scratch space to read into. And what are these? These are dir link things, so we don't have a data structure to read that into. Well, we can copy it from here. Where is it? It's a dir link. Okay, what's interesting is in the, like on disk, the name is right here. I mean, I've been avoiding trying to do this, but that makes things easy. So can we do this with like a single dir link? Right, because we have, we're at the root inode, which we know is slash, so, you know, our path is going to be this so far, and then for each entry in there, you're going to have its name, so you can read it into one of these dir link things, and then go like, alright, well, combine that with this. So like, I don't know, like documents. Then you can compare that with this. I mean, we're thinking only about the case where you're not trying to create a file. I guess in either case you need to see if it matches one. So yeah. So how do we want to do this build up? Well, you could just say you have a buffer. Do we need a 0 initialize? I mean, whatever. Just thinking how we want to handle this. There's a bunch of ways we could do this. I want to do it like... It's weird because I'm in the kernel, so I don't have user space utilities. You know, so we're gonna need this thing. Right, and we need a buffer for the, so actually, you know, we can have like a block buffer we need to read all that into, because we can only read a block at a time. The reason I'm having a bit of trouble is because we haven't really thought about memory management in the kernel at all. You know, and here we have a page allocator that gives you pages if you want dynamic memory, but what we kind of want to do is, I mean, what we really want is to have a scratch space where we can say like, all right, read into this buffer so I can do my processing and then have it disappear at the end of this, which is basically an arena. We could do, we could make like a little arena in the kernel that's like, how do we have like alloc pages. Okay, so let's see. So we need to read the root inode, which is a directory, right? Directory on disk is a list of dir links. How do you know it's the end? I mean, I guess you have to know in the inode it's how many. Yeah, so go to the inode table, it tells you how big it is, then you read each entry based on its entry size. It actually works, both of these work if we just make this. Yeah. How do we want to read that? That's the question. Just trying to figure out how much effort I want to put into doing it right versus just like getting something done right now. You know? Um, It's gonna be there. It'll fail. Alright, so if we read the first block of this little bad company, or Nazareth, I mean. Let's see. Read in a block at a time. Alright, now we need to parse this block kind of, so you have the current link you're going to look at. what do we call this, right? So the open syscall gets a path passed in, and then we're building up a thing to compare it against. What do we call that? I don't know. Current path. What kind of stuff do we have? This is basically like our libc. So let's go back to what we were looking at in the Dirlink. So you're gonna have entry, name, and you know the entry size. Well, we can use the name size. We don't need the entry size really in this case. So we need to pin that to that above. So like, should we do this in common? Maybe. What I want to have is the same thing we did here. We want this and this. Right? But we don't have stern copy or what's that? Oh yeah, that's fine. We have Sterling and we don't have S in printf. Which we don't really need because all we're doing is that, so we can probably implement a version of this. What we'd like to do is this. I guess you're building a new one every time. You want a path join. Entry name, which is entry name even null terminated. I don't know if that's guaranteed. So I guess in this case we're gonna need name size. And then I have stir comp, right? I did implement a stir comp. So if they match, then we found the file we want to open. So, you know, the other part of this is you have an open file table. You need to first walk that. You know, which makes me think, like, let's see. Open files. It's not actually like is this the open file table or just like the file cache? You know, like files we've already read into memory. What do we have in a file? That's gonna go away. Yeah, this is all old data. What do we actually need in a file? You need a file offset, right? These are basically the things you need. An offset flags and a inode. Okay. Inode num. Perhaps a ref count, its size, and the current offset. Ref count we don't really need right now. Well, yeah. This is interesting. I don't know the best way to... So, you know, you're going to have a file, open file table, which has a bunch of these, right? So, if you are in here and you find, like, oh, this is the file you want to open, then what? Do we have to walk the file table to find the one with the matching inode number? Which is fine because you can only have 128 open files, but seems interesting. So you want something like... Alright, I think I have a little bit of an idea what to do now. So you need to look in the current, so in the you need to allocate a new file descriptor basically for this, and so in this process you're gonna have a file descriptor table that points to the open files. So you need to look if you have an open file already. That's great. You can give a file descriptor that points to that. If not, you need to create one in the open file table, put it in there, and then give create a file descriptor that points to that. So you have a current proc, descriptor table, num descriptors, fd, num FDs. I don't know, that looks kind of dumb to me. Have FD count. It's just I use num thing everywhere, so we'll just keep it consistent. So a file descriptor we're gonna call an int because it can be negative on the case of failure. So file descriptor is current proc. It's that one, then you bump it. And then you can say, well, current proc descriptor table at FD. You need to just make sure you have the right pointer. It's really just a, yeah. Equals what? Well, you know, if it's already open, you can give a pointer to that and bump the ref count. If it's not, you need to create one. So do you want to do something like find open file thing or whatever? No, we'll just do this. So you're looking at this entry, inode num. So if this is equal to that one, you found it. It's that. And I mean, you can break out of the loop. Should we wrap that in a function or not? I don't know. We can if we need to later. So if we don't have it yet, well, then we need to make a new one. So open files at num open files. I mean, we really don't want to be doing this like this either. We want to say like well, hold on. You need to know if it's a file or directory. What does it mean? Alright, just assuming it's a file right now. This will be in the case where it's a file. The inode's what carries the size. I mean, this is gonna be like base. Yeah, and then so you've got the dir entry. And then I guess you want like yep. Right, we changed this to accept a message. I don't know, something like that. So you have the inode. The reason we need that is because entry inode. This is where you have the size bytes. Why do I have size and bytes there, but just size everywhere else? Because, yeah. We'd like to have something like this. Something like that. Alright, then, alright, getting a little bit lost. Alright, so if you find one that matches, then, you know, see if it's open already. So that's what we're doing here. If it's not open already, well, we're gonna make a new open one. Okay, and then, so, now you have file for sure. Yeah. So now you can do this file. All right. You can also mirror that and say append. Alright, so where's all the other proc stuff we have? Well, you just do I mean, we don't have to. So if that's the case, you know, we're gonna return -1, but this is a terrible message, whatever. Jesus Christ, okay. Return -1. Oh, it's, well, we just say, current proc at, scripted table. Num.fds ++ is file. Rather, it's like this. Okay, so we do that here. I don't know, like set Arno or something. We don't even have a concept of Arno yet, so if you fail to pin, it's just like max We'll just print a thing here for ourselves. Alright. As max file descriptors. Cannot open. Something like that, I don't know. Build to open path, rock, current, rock, bid. Yeah, and I think we actually want that. Here. Are you doing that? Should we do it like that? We lost track of the file there though. We actually do want to do it there. But then we don't want to do this here. That's what I wanted to do. Okay, yeah. Whatever. And then we need to set that in A0. I guess we need to cast that to U32. That'll auto cast, but like Ant can auto upcast, so that's fine, but make it explicit. Maybe not. Oh shit. Well, it doesn't matter. It doesn't matter. Like, on the other end, we're gonna have to cast it to Ent anyway, so it doesn't really matter that storage is U32 in here, but okay. So that's where we put return values. So we're starting to have something that looks like an open syscall. Alright, we still need to implement some of this stuff. What is this? Like, we still need path join, we still need append open file. Let's do this one. Oh, that shit's down there. Let's put these here. And then we can also do, what is it? This one, append open file. Alright, append open file. Takes an inode num and a size. Well, you need to say, you know, same as here. Except it's if num open files can't do that. Otherwise, what are we gonna do? Well, open files at num open files. Sure. I don't know. God, I'm tired. I can't fucking type. File ref count is now 1. Size and size. Offset is 0. Okay. Alright. We can append open file. And if we still have no file, well, we failed to open this. Already has max files open. And we're just gonna return -1 break. Shit, we're in a for loop. Damn it. God damn it. This is what... Alright, how do we... Where are we at? We're going through... We're reading block by block. So if you found it... You break out of the center for loop, that's fine. I don't like that this break, you know, this for loop, it looks a little... Alright, that gets rid of that ugly ass break here that's confusing. So, open file from inode num. That's a little confusing though, because it seems like this like might open a file. But no, we follow the convention that it's like, you know, type that you want from type that you give it kind of thing. So like the thing you're getting back is an open file, not doing an open file. Alright, that's probably fine. Okay. So, you don't want to do that. Break. That's a little more readable. Alright, we're still in this loop, right? So the weird thing is like, you've cast this entire block to a single dir entry. We need to like iterate the dir link entries in this base. So the way you do that is like, you know, size starts at 0, you go until size is like the inode size. So like I mean, I don't know if this is gonna work out on a loop, but it's something like this, like base inode size. Should probably do this too. A little, not very readable. All right. We're gonna have to do the increment in the loop. So we have another loop. So we're gonna have to break out, we want to break out of this loop. So once again, we're probably gonna have to do this at some kind of function. Rather than, you know, you could also have like a label, but the whole function is like this. We should probably make this like we could do this. This will make everything better, I think. What's this? Alright. Now things are way better. Alright, so so this is what we're trying to do now. So if you hit this, now we can just straight return -1. And here, okay. Turn this file descriptor. Alright, so alright, here's an interesting question. What's the size you get if you take size of a structure like this that has a, like, what's the name of this again? Variable length array or something? Or like varied array member, something like that. VLA? Variable length array member? Anyway, if I take size of this, what do I get? Because what I want to do is say step forward by these and then add entry size to it. It's like, what I want to say is like, it's the size of entry. I mean, that would be great, but since this, you don't know. I called it entry. Gross. So it's entry size. What a line. What, like, look at this. Total entry size is size of entry plus entry size. Ugh. Whatever. Total entry size. This is confusing too. We should call this name size with padding. So now this is name size with padding. But now what I need to verify is if you call size of with this, what do you get? Yeah. Well, let's fucking test it out. What was that? Where's that type? Their link. Okay. We don't have these. I mean, it doesn't matter. The ents. They're unsigned, but whatever. Doesn't matter. I just want to say. Size is this. Size of a Durlink. What do we get? Size is 8. Eight bytes. So this is 4, 5, 6, 7, 8. So 0 size. You don't get size, which is actually what we want. But that's only with MSVC. But shouldn't it be standard? Should be, right? I don't know. We're gonna hope so and see what happens, you know? We don't have remove. What is it? Delete? Ah, God, didn't it poop out a bunch of other stuff? What else do we have in here? Did it poop out a bunch of stuff in here? You don't need that. Is there PDBs and stuff? Delete that. Oh yeah, I didn't include debug information, so that's all that was in there. Okay, so that's actually what we wanted. So it's just size of the entry plus entry. Name size with padding, cool. So step the buffer forward by that many bytes. That should get us to the next Durlink. The only problem is, are these aligned to 4-byte boundaries? That's the question. Be right back. Gosh to pee. Alright. Damn it. What we was doing. Syscall open. And then we wanted to look at these types. Okay. So, I'm feeling very tired. So, I have grabbed this Ferrero Rocher. And if I'm able to finish this system call, I will get to eat this. That's my motivation. Alright, let's go. Where are we at? Where were we at? I think we're trying to like do this directory link entry thing. So it's weird because like you just have like variable sized. We were trying to see if it's aligned up to 4 bytes. We need to make sure that's the case. So if we look where we write it out, when we write entry, if it's a directory, what do we do? This is interesting, because if we would have used the VLA thing there, maybe it would have been, whatever. So, data size is size without name, plus entry size. It is aligned up to 4 bytes, and you're just assuming that size without name is also, so why wouldn't we do the add and then align up to 4? Just in case. Because right now, it's just 8 bytes. Either way, it is aligned up to 4 byte boundaries, so we need to make sure that that's the case too. So Total entry size is size of entry plus name with padding. This whole thing needs to be aligned up by 4 bytes. Yeah. Alright. Do we... Please God, tell me we have a line up. Oh yeah, Risk 5 has built-in align up, doesn't it? Okay, or rather, it's the compiler that has that. Yeah. We're using Clang to compile this, right? So it's Clang that has the built-in align up. Okay. So we step that much. Now we get a new entry. See, the thing is path join modifies the path. We just need like how are we gonna do this once we start going into? So this is just for a single, like a flat directory. But we need to recursively like traverse, or not recurse. Well, yeah, we need to traverse subdirectories as well. Something like this. Something basically like this. But let's look at a single one and see how this looks. So this is all of the entries in like this base inode, which is root for now, right? And I guess this is just we do that. Alright, so we read a directory link, or rather like an entry. We get the inode. We append the path of that to the current path. Then we compare and say, is this the one we're looking for? If it is one we're looking for, see if we have an open file already. If not, open a new one. Then we create a new file descriptor for this in this process. Set it to point to the file that's in the open file table. And return it, right? But if this is not the one we're looking for, what happens? Well, we step to the next entry. You have a new entry, but we also need to reset the like path. I mean, we could just drop a null byte in at like where the old one was, but let's think of how do we want to handle this. Strings and C, man. So, okay. I think you actually are gonna do this. Whatever current path is this, then you want to say path copy into current path root path. So Sterling doesn't include. So we could do this. This is going to be different in this because. Yeah. It's going to have to change, but for now, since we're talking about root, let's call it that. Substitute for base root. Root inode is that. So copy this into here. Now we can. In fact, it's actually this, right? That was right. Hold on. Yeah, let's do it here. Yeah. So you copy it there. Can maybe do this. So we build the new path, the current path, then compare it. Just a bunch of stuff we're not handling in here. Like we haven't even touched flags, file mode. Ooh. We're gonna call it success if we can just like find the file at all. When we call like open, it's just gonna search for the file. If it finds it, you're gonna get a new file descriptor in the process. So we're gonna shoot for that, so I can eat this. So let's go. The thing is, we're not handling like subdirectories, so this is this thing we need to do for every. This is the thing we need to do for each base, like each directory, each subdirectory. You know, should we look at some of these errors? Don't have path copy, path join. These are unused. These are unused. Okay, so let's implement those. mean, the advantage to doing this is like it always writes zeros, you know. So what's it say about stir in copy? Interesting. That's one way to do it. Wouldn't, if you did this, it do the same thing? Oh right, it's looking for, yeah, what do we do? Yo, Zen, what's up? Another day, another dollar. Yeah, another day where it's 2 a.m. and my brain is failing me. I'm trying to finish implementing this so I can eat this chocolate. That's my motivation right now. And I'm lost in minutia right now. I'm just worried about shit that doesn't really matter. Like, I don't even really need this fucking normalize right now, but that's what we doing. In fact, we ain't even gonna deal with that. So, we need path copy, we need this path join over here. Do you have an official work? Where are you from? I got laid off a couple months ago, so yeah, that fucking sucks. I live in US. Yeah. Alright, so, well, first of all, we need to implement the stern copy. That should be pretty easy. We'll make one of those. So, user space. Actually, it's in common, right? This is basically our libc. So, we just need a size. Stir copy. Alright, you want one of these that says the same thing as this, right? Except you're saying iterate through source until you hit, what is stern copy? It's up to size, or if you hit, because you could hit the null byte before then. Or is this about this? Yeah, here. Right. But not any of the characters that follow the null character. Yeah. So if count is reached, it's not null terminated. If after copying the null terminator from source count is not reached, additional null characters are written. Okay, so yeah, we need to do this. We copy from source until we hit a null character or size. Right, like and size less than size. Then we say, well, there's a few cases, like, if I is still less than size, we keep writing null bytes in. So, we can just do another one of these. So... just keep writing null bytes. If there's any left, we do that. And then, what was the other saying? Like, alright, if you reach... If you reach size before end of source... Wait, what's up? You know how to code in C++? I mean, kind of. I like C, so I try to avoid like C++ like the plague. Like, I don't like the whole object-orientedness that you get into and like the modern C++ style. I don't like that, so I avoid it. So I'm not super familiar with all of the craziness, in my opinion, craziness of C++. But I mean, I can like understand, like, I can read it, I can write it, but I'm not strong in C++. And then we don't do that. So like, if what did it say? It said if you don't write the null byte in count is not reached. Okay. If count is reached before the array was copied, the resulting character array is not null terminated. So it's like if size was reached before this, then there's no null byte, which this does. So alright, this should be stir and copy now. So we have this, we can path copy now. It's fun. Are you a C++ programmer, or what's your flavor? What do you like? Yeah, path join. No, we're gonna have a size here. So okay. Why are we using SM for that? So this is saying, we go to the end of the string. If it's not like the root and the previous character is a slash, then back up. And then, are you doing this for some reason? I'm just trying to learn how operating systems work. So, you know, I'm making a little tiny one. Just curious. That's about it, yeah. For learning. I feel like, when you get in the gritty details, then it's like, I just feel like the understanding is much deeper and like, you know, makes me a better programmer. So, that's what I was doing. Alright, so you're gonna go to the end of the string. What is pointer? Oh, yeah. So this is in the output. You go to the end. The weird thing is, why would that ever work? Like, why is that looking for... Because if that was, if the path was root, then path plus size still goes past the root. Isn't that what this is trying to say, or is this trying to say something else? That's not root, that's just saying if it's an empty path? Is that why? Yeah, because you might want to, well, yeah. You might want to join into an empty path, but then you just path copy, right? Which role and language was your last job in? Well, I started, it was like, mainly like web dev type of stuff. But the role transformed a bunch while I was there. I was there for a long time. I ended up mainly writing like internal tools for my team, and I could use whatever language I wanted. But well, kind of, you know, I ended up writing a bunch of tools in Go. I wrote a bunch of Python, but when we had to do client work, I would have to use whatever, you know, there's a lot more restrictions on it, but yeah, not because I'm interested in web development, it's just, that's how I got, you know, your foot in the door as a programmer. You know, back when I started there 8 years ago, I didn't like know really any systems programming at all, so it wasn't even an option to find roles there. And now it's kind of hard to find, like, things that are interesting in programming to me are not where jobs are, so it's like, what do, you know? It's tough. Also, I don't know fucking any, I feel like another huge part of finding, like, in any profession, like, having knowing people is super important, and like, the list of programmers that I know is like basically zero. Like, I don't even have any friends who program. I didn't go to school for like software engineering either, so computer science, so yeah, like, it's a little bit tough out here. Yeah, alright, so you step forward in the source. C is your main language. So yeah, I mean, C is what I use recreationally, I guess. That's like that's my like what I use on my own projects, but I've never worked in C professionally, so yeah. But I mean, I have a few projects that I've done in C. Like, I've written a compiler and a NES emulator, NES emulator, and a bunch of little games and stuff like that. So. What about you? What do you work in? Slash, like, play in, I guess. Do you have like personal projects and stuff too, or you just work professionally? Yeah. So we don't have S in printf either. Oops. I mean, we do have this. Which I don't really want to do. You're building a distributed system in C++. Interesting. That's something I also don't have any experience in. Distributed systems. That's like some complicated stuff. Interesting. So how do we get rid of this S in printf? Well, so pointer is currently at the end of this, the last slash. You know, if there's a trailing slash, you back up. So yeah, this is just like a... Interesting, what's going on? It's hard stuff on software development. But I was full stack engineer for a long time with interpreted languages. Now I'm trying to go deep on compiled languages like C, but C doesn't have any easy to use libraries to deal with async systems. That's true. Well, C doesn't have a lot of libraries to deal with. Well, it has a lot of libraries, but there's like nothing built in. Yeah. Deal with async systems. Yeah, I mean, I feel like most C programmers have to build their own little like library of shit to get anything done with. But with async systems, yeah. Wait, what is this? Hold on a second. Alright, sorry, I got a call. What was I saying? Totally lost what I was happening, but alright, we'll do this. This is just saying, wherever you are in the source, the problem is when you build a level, you're mainly responsible for everything. Function across your system is over. Yeah, I mean, depending on system, but yeah, you have to. It can be like high stakes. You gotta be pretty careful. I mean, that's kind of what's fun about like doing recreational systems programming. It's because like you can still play around, you know. But yeah, I know what you mean. All right. So we just need to loop through the end from wherever we are until we get to the end of which one? End of source. Okay, so so yeah, we just copy the whole thing in, right? Easy, easy as, easy as, easy as. Well, you're starting from here now, so this is like your new. What's that? Or you could do. How do we want to do this? It's basically like this character is gonna be this one. One question: all the variables on stack and see. I mean, it just depends on what you do. By default, yes, but you can do like dynamic annotations too. You either call malloc or you can use like an arena. That's what I would typically do if I was like application code. It's a little bit different here because I'm like writing the operating system, so like in the kernel I don't really have much in the way of like, you know, all you have is a page allocator, so you can allocate a page at a time. So like doing stuff in the kernel is proving to be interesting because like you have a little bit more restrictions than you normally do. Half of yesterday and like the day before, I was like implementing dynamic memory on like user space side. So you have malloc and realloc and stuff. So yeah, so I mean, all of these are on the stack. Everything I've been writing so far, basically. But yeah, basically you call malloc to get memory on the heap. What I would usually do in like my stuff is like when the program starts, you allocate a big fucking chunk of memory. Or actually, the real like smart thing to do is use like virtual memory to your advantage and like reserve, like use OS facilities. Like Linux and Windows both have facilities to be like, hey, I want to reserve this giant like address space up front, but then only, you know, allocate it actually, like back it with physical memory when you touch it. And so you can, you know, basically allocate all the memory that you would ever need, and then your program can use that like an arena and just bump a pointer every time. That's the way I like to operate, but yeah. But right now, we're just doing everything on the stack. So yeah, so you go through these. Are there problems with alignment like on C++? It just depends on what you're trying to do. I mean, what specifically do you mean? Like, you just mean like reads, like reading a struct or something that has to be 8-byte aligned so that pointers are aligned and stuff like that? It just depends on like right now I'm dealing with that a lot because like since I'm running the operating system, I have to make sure, like right now I'm just reading in like from the file system, right? Like the way directories are stored on the file system is like basically lists of inode numbers and names, but a name is variable size, and so the name could end up at a place that's not 4-byte aligned. 4-byte because this is a 32-bit operating system. So you have to make sure you align everything up to 4. But like in general day-to-day stuff, I'm not really thinking about alignment that much. or ever really. I mean, yeah. Or unless you're thinking about like alignment of like members and structs too, to make sure that like it packs tightly. I mean, that's usually important if you're like doing serialization type stuff, where it's like important that you don't have space, so you can like read and write to disk and on both ends have the same thing. But yeah, I'm not sure exactly what you mean if you want to specify more than that. Okay, we go through the whole size. So if this is this, we and decrement size. And then the other thing we have to be careful of here is that we don't run out of characters for pathmax 2. You interpret kind of structure. Yeah, I mean it's the same in C, but I think isn't that like a processor specific thing, not really a language specific? 'Cause it's like, can the processor read unaligned memory is the question, right? Not totally sure. So how do we want to do this? Basically, we want to say like if it ends in a slash, we leave it. If it doesn't end in a slash, you have to add it, right? Because you're just trying to combine these two paths, so. If so you remove it from the destination. Okay, then you say you add it in. We can even do this, right? Alright, add it in, and then copy this into there. We just have to be careful about Are you publishing code on GitHub or working like? I mean, yeah, everything's on GitHub. I don't think my most recent changes are, but. I mean, this is it right here. Yeah, it's outdated, but I can push it up after this, but yeah. Oh man, I really want to at least get like the Open Syscall finished, but I'm struggling. I feel like my brain is going 1 fucking mile an hour, but I think I can do this. Okay. Oh, I keep fucking spinning on this stupid. I've written this function like 5 times before. Alright, so we go through, what I'm making sure that I'm like not overriding too many characters is the question. So you go to the end of this, if there's that, you back up. Alright. Clean this up and make sure that you don't write more than path max characters. We know later, but otherwise this should at least join the path, so we have implementations of all of those, right? Alright, we got warnings. Unused parameters, that's fine. We have unsigned and signed comparisons, that's not good. In common. Because we have a U32 size, so we can use U32 for that. Alright, make sure these are safe. It's really only a problem when you have like minuses and stuff. Or negative numbers, so that's good. What other warnings are they just unused? 942. Right, this doesn't return in all cases. Yeah, because we're not done implementing this, but... Once again, we have unsigned, so we'll go with that. Okay, so that should work. Can we do... a... So this is just going to read through root. What do we have in there right now? Hold on, let's see this. So in root, there's code, documents, and a text file. So... if you reach here for some reason... we didn't find the file. We'll just do that for now. Okay. Now, let's go through this, make sure syscall open makes sense. Right now we're ignoring... what we want to do tonight is just say All right, if we call open with a path, and to start with just in the root, can we at least find it? And then create a new file descriptor and the process for it, and create a open file for it, a system-wide open file in the open file table. And can that map back into the inode table correctly? That's what we need to be doing. So, the way we do that is, alright, we start at the root inode. Then we have a path for that. Then what do? We start reading blocks. We should only have one, but you know, you gotta loop through them all, so you could have more. Then what? We need to read all the dirlink entries in. So, you know, we have to read a dirlink entry. Then get its inode. Start building up the path. So you just append whatever this entry is to the root. Check if this is what you're looking for. If it is, we open up a final table. Makes sense to me. Alright, so surely this won't work, but let's do this. Once again, we do this trick. I'm just gonna do this. In user C, we have open, right? Yes. Okay. Notice. So the working directory, I guess we'll just give the full path. Flags, it doesn't matter, we're ignoring them right now. Alright, and what do we get? Undeclared function open. Why? Do we not have that? Unused parameters, that's fine. That's interesting too. Yep. Interesting. So we tried to read this sector, but we only contain this many sectors. What does it say? Ride to... Okay, so it's in this. So it's clearly in disk read block. In here. So let's see. The root inode is inodes 1. And let's see. The inode table started there. So the first entry should be this. The type is file. This doesn't seem like... the root inode. Type size num adders is this, and then what's the first one? We'll print that. What we want is actually this. So this one. Type, size, no matters. This is one of the things that sucks about C. It's like your language should really give you like stuff like this, but I mean, C was made in the 70s. It's like it's just how it is. So inode adders 0. So just print. We need to print inode thing so we can do this. All right. So what do we even have here? Right, we don't actually want that. It's just, that's a U32 as well. But we print it like this. Yeah, alright. Okay. So, type 1, size 0. Why is root inode size 0? This is the offset, so yeah. Code, documents, and notice.txt. So like this is fine, it's just the size is fucked up. Why does the root say size is 0? Well, probably when we created the file system we fucked up. So let's see. Right. Right, entry. I just want to see something. I don't think we're writing out the size for directories. We're only writing out the size for files. That's our problem. Yeah. Okay, so if it's a directory... Well, where do we write that? So do we have it? Inodes. So if it's a directory entry, or if it's a, yeah, if it's a directory, it's size in bytes. This is where we do size in bytes for files. But for directories, we don't do it till here. That way we also get root. But we don't know the size yet here. But you do have the inode, so what you can do is this. Alright. Wait, why do you have... Because you call reader on it, that's why. So this is where you have the size. I'm just trying to make sure we get the root too, because we could do it right here and you'll get all the children, but for root, the root one's not a child, so what you probably have to do is up here do like a stat, like which is what this does anyway, right? Ooh, we did OS file size. Oh, wait. Yeah, that's why. Because you won't know the size until you write it all out. So we should do it here. I guess, yep, that's why. Here. When you're writing an entry, if it's a directory entry, then data size is going to be this. we want to make sure we right out on the thread links. Why do we do this? Size without name plus the lineup, link. Anyway. I don't know why we do that twice, but it doesn't matter. Okay. We're gonna make, do we have the inode? Yeah, we're in here. If it's a dir, we need to say num adders, and then for shits and gigs, we gotta make sure we have the size. For the directory, we say inodes entry. Oh, we have data size there, so we can still do here. Inode size is data size. That's all we have to do. Okay. Alright, we're good now, I think. Size of non-member disk inode. We called it size in bytes here, I think. Yeah, size in bytes. Okay. Now it looks like we have a size. Let's see. Okay. Now we have the root inode is type directory, size is 100. This directory is size 72. Alright, so those are valid. So we fixed one problem. So then what's going on? So we know that no matters is 1, right? Let's just keep printing this root item. Yeah. So you know this loop's only happening once, so what do? We try to read it in. Oh. Yeah, disk read takes a block ID, not the address, right? So yeah, that's a problem. So why is this here? Yeah, wait, what? So we do need this, but so num matters I is a block pointer, right? Because alright, so what we need to do is this. It's like this divided by disk block size, and we should probably do it like this. Like block ID is this divided by disk block size. I just need to verify that an inode adder is for sure a it points to a block, like the beginning of a block. I think we should be fine. I think we verify. I think we ensure that it is. So that should be okay, I think. Okay, now we got a new issue. Now we're getting a load page fault. We're trying to load this value. Why did you start from the file system first? Well, I didn't. I made like a super simple version. Actually, the original version was using like a tar file as the whole file system. And so one of the first things I wanted to do as like an exploratory thing was like swap that out with an actual file system. And the other reason is because like it's a thing you can like easily play with and interact with. So it's like, you know, I have the like, so the tough thing is like there's a bunch of things that need to interact. And so starting anywhere, you have to touch a lot of things. So like what I want to have is a shell that I can like type commands into and poke around and interact with the operating system, right? And so in order to do that, I mean, you need a file system so that you can like poke files. You know, the main things you want to do in a shell is traverse the file system. So it's basically that, you know, like I wanted to be able to like have a little playground to toy around in, and like the file system and the shell provide that, and then like in order to have those things, the kernel has to provide a lot of like facilities to both of those. You know why when we talk about something complex we feel like if something hit us? What do you mean? Hold on. You know why when we talk about something complex we feel like, you mean like it's really, yeah, like it's hard to talk about and you're just like, is that what you mean? It's like hard to explain and put into words, things like that. Yeah. Also, when you try to talk about something complex at like 3 a.m. and your brain's not working, it's like, ugh. Okay, but I really want this. I want this to work. I feel like we're close. Okay. So we're just getting a load tree file. We're trying to load this, which actually kind of makes sense, right? Because it seems like, well, actually, hold up. Yeah. This should be okay. This should be okay. I think I know what's happening. I think what's happening is like the operating system is trying to touch memory. Well, no, it should be trying to read from disk. Where's this address coming from? It's on 105. Yeah, it's coming from here. So who called this though? Why are we getting a load page fault? Well, let's see. We're trying to access this address. Isn't that in the user heap? Where's my offsets? User base is here. Not the user heap, but the user's process. The address is this. Yeah. So what lives there? I mean, this is where an application image starts. So what's in there? Is that where we map kernel pages? It's weird that we're hitting like user space memory from the kernel. I mean, I know that there's kernel memory that's mapped into user space but marked like not user accessible. But why would from an open system call, where are we trying to use that address? I mean, is it when we're trying to do this disk read? It's gotta be. So when we read in here, I mean, we don't hit this assert. Into that buffer, that block. We call this vert.io read sector. It's gonna do a read. You do a mem copy into that buff. Is there no way to get a stack trace? Well, since this isn't running on like Windows or Linux or something, like there is no like facility to do that unless I implement it, you know what I mean? Because like this is the operating system we're making, and it's like there's no stack trace like built into that yet, so I don't really have a way to do that. That's why I have to do all this dumb printf debuggies, because there's just like not facilities built in to help you debug yet. Because like, I mean, it looks like it's running in like just a shell, but like this is actually running in QEMU, so like it's you know, emulated RISC-V 32-bit CPU. Yeah, I see. Like this is the what it's running on, and the operating system that I'm making right now doesn't have any kind of stack tracing stuff, so. So let's see, when we map pages, when we create a process rather, and then we map kernel memory in, what are the pages we're doing? From the kernel base, which, where is that? It's defined in the linker script. So this is the kernel base, yeah. That's definitely not where you're reading from. You're trying to read like user space memory. Why is that? Why is that? What's happening here? Map the user pages, right? I mean, is it because... No, it's got to be the disk read block. Where's that buffer live that we're writing it to? Is this the problem? No, we should be able to write into static memory. My brain is failing me right now. Do we have to... Hold on. If we do this, do we get the same? It's not that. I mean, although you're onto something here. We can do like this little, you know, we can trace where we are with printing. So like, yeah. See if we even get to. So we make it through all this before we get there. So where is this happening? Oh my, wait, no, that's fine. Yeah, so we don't make it there. So it happens while we're reading entries in root. God, I wish I had a debugger. Where else are we touching memory? Is it... Alright, we're just gonna do the dumbest, like... No. What? So that's right. So our path copy and path join's working okay. That's good. Well, maybe. Wait a minute. It's not. Oh, classic. You have entries dot and dot dot. Should these be written to the disk? No, right? It's so stupid. I mean, we're explicitly writing them there, but why? So we... Did I make that? Yeah, I can't think about this right now. We'll just do this. Right now we're not gonna have hidden files, so we'll just do a stupid thing right now because I gotta get this done. So if entry name, if it starts with that, we're gonna ignore it. No. This is stupid. Do something better. We still need to do this, so we either do a go-to or we do this twice. Cool. So we skip dot and dot dot. Can we not have labels? is going on right now? Okay. So that was the reason we were getting load page faults somehow. Probably because you were trying to go to ... in the root, which doesn't exist. So you're trying to read memory like, I don't know, outside of it or something like that. Okay, so invalid inode. Get another call, hold on. I gotta go take care of something, hold on. I have to go. I got home issues I gotta deal with, so I do not get to finish System Open Syscall or eat this chocolate, but you know, we'll try again another day. Alright, peace.